Welcome to Driven. I'm your host, Paul Perrone. We're going to learn and talk about AI, robotics, autonomous vehicles, and so much more. Check us out at driven.show on the web and give us a thumbs up or subscribe here if you like the show. So kick back or buckle up and become driven. Paul Avery, hey, thanks for joining today. You're a guy who's been in the trenches of autonomy now for over 2 decades, like myself. And I, from building, I think, multi-agent autonomous systems at Southwest Research Institute to heading AI and machine learning efforts at the likes of GM, and you're now steering automation strategy, I believe, at AECOM. So I'd love to hear about all this, and you've seen the evolution of connected and automated vehicles from DARPA, as we all have, as I have. 20-year anniversary just cropped up for the 2005 DARPA Grand Challenge to nationwide deployments. So I'm just excited to talk to you here today about what happens when AI stops living in the cloud, right, and starts driving cars and managing traffic and reshaping how cities, move and how people get around. So it's great to chat, wax futuristic, dig in a little bit into what you're working on and see where the conversation leads. So thank you for your time today.
I appreciate the invitation. I've seen the podcast, as it's been developed. Obviously you're a name that I'm familiar with because we started similar timeframes. And I think we're one of the very few that have continued since that time frame. There are a couple other names that kind of are still in the mix from the DARPA days, but not very many. 20 years it is for me coming up. I started 20 years ago, 2005, not for the DARPA challenges, but at Southwest Research. So the reason at that time I had essentially gotten out of grad school, and my interest was in the behavior of decentralized systems. I mean, that was my interest. So in grad school, I got to study insect behavior of all things, but I'm a mechanical engineer. So, when you have an ant colony or a beehive, they do very interesting things, and there's no central committee, there's no planning committee, this type of thing. So how do they do it? That was my driving force behind this behavior of systems that are not centrally controlled. So when I joined Southwest Research, within about 6 months or a year, DARPA announced the challenges, or they had already been announced and they were kind of underway. But at Southwest Research, we saw an opportunity not to participate in that specific challenge, but to take kind of a first principles look at, well, how do you make sense of the world using different types of sensors? And make sense is a very, it's a phrase that humans understand, but how does a computer make sense of anything?
Right. Perceive, right? Perception or whatever you call it. Yeah.
Yep. So the perception of the world, and then translate that into meaningful context, and then take an action that is appropriate. Again, all of these words are loaded. So we took a Ford Explorer because we had one. I mean, that's what we converted into an automated vehicle. And so that was kind of my introduction to automated vehicles. That vehicle that we worked on is now sitting in a museum in San Antonio. So, if you're ever in San Antonio, the Museum of Science and Technology hosts that vehicle now.
Cool. That's a Ford Explorer, and so you all outfitted it from scratch, right? From the drive-by wire and everything. Yep. So, interesting. And that was right kind of concurrent with the DARPA Grand Challenge, the 2005 one. Is that what you're saying?
So we started kind of preliminary research in 2005, and then we started sort of building it in 2006.
Okay.
And there was, Southwest Research is an interesting place. If you're familiar with it, They are a nonprofit applied research and development entity. So they fund a lot of internal research. It's competitive. You have to develop proposals, etc. Well, this effort was so big, it couldn't be any one set of researchers, or one division is what they call it in Southwest Research. So multiple divisions came together. There was a big down select process there. And there were just a handful of us that ended up getting dedicated to this project. So again, my interest though was in the behavior systems, right?
So just if I could ask, like, and if you're able to convey it, because it sort of speaks to the magnitude of the problem back then and even today. Like how big was, if you're able to speak to it, how big was the team? Like what was the budget, for a project like this, like in 2005?
So that's the funny thing, and that again forms my opinion on a lot of things today. There literally were 5 of us that were the core team, and there were another like 5 or 6 that were like advisory, strategic level. That was the down select. So that was the team.
Okay.
The budget, the entire project, which was multiple years long, including hardware, was the biggest IR&D, internal research and development project at Southwest Research, and it was $4 million. 4. That includes the...
Yeah.
So we did a lot with that money, and we didn't... It's kind of like we didn't know any better. We didn't know, hey, in 10 years, 20 years, people are going to be spending billions of dollars on this. We kind of thought maybe they would, but we had a little budget. Let's figure it out.
Yeah.
And my interest was in the behavior architecture. So that's what I focused on. I did get into the sensor fusion, stuff like that. Since there weren't a lot of us, we all kind of wore multiple hats, but my focus was behavior management and architecture. And that informs my opinions today on this stuff.
And was that your origin story, your personal origin story with sort of robotics and intelligent systems, or were you doing something prior to that? Or was this sort of like diving into the deep end kind of thing?
Yeah. My bachelor's and grad and master's are all in mechanical engineering.
Okay.
But I wasn't really interested in designing things, although I did do that. The reason I went back to grad school is to do some other cool stuff that had to do more with these esoteric concepts of decentralized control. And my thesis was on the decentralization of the electric power grid and how you can make it more robust and this kind of stuff. That's what caught SWRI is how you pronounce the acronym. That's what caught their attention. But I came in and I was helping design machines, right? Because there's not a lot, there's not a lot of work for decentralized control at that time. But when the automated vehicle idea popped up, I mean, I jumped on it. I just had it. That's what I wanted to do. I knew it. That's what I wanted to work on.
Interesting.
So we had that vehicle in New York City in 2008, as it demonstrating on the streets of New York City at ITS World Congress 2008. And so a lot of people, when I talk to them and they think all this stuff was like circa 2014, they think that's when it kind of popped up. I'm like, oh.
Yeah, no, I know. So that's interesting. So New York, it's funny, back then, a lot of folks were like, certainly government and city and organizations were, naive to some extent. I didn't know what was going on. So like I would drive, which is completely a non-street legal vehicle, Tommy, our dune buggy, like around the roads here in Virginia. And like the police would pull up and say, you would think they were going to like try to arrest you, but they're like, what are you working on here? And so it was more of an interest. And nowadays it'd be like, all right, get this driverless vehicle off the road without a license, maybe. But interesting in New York, especially, whereabouts in New York City were you driving this vehicle? Was it like around a block? Was it like, I assume it wasn't through, Broadway or anything.
No, so the MTS World Congress, they was at the Javits Center, and they
Okay.
blocked off the roadway in front of the Javits Center. So it was about a block and a half that was blocked off just for vehicle demos. Now, if you've ever told a New Yorker they can't cross the street, you know that's it's like trying to tell your cat not to climb up.
I'm walking
Right.
here. It's the famous
Yeah.
scene from Midnight Cowboy, but
Yeah.
Dustin Hoffman.
Yeah. So we had people still walking out in front of our vehicle, which is like our vehicle's fine. It's like, oh, if there's a person, an object, I'm going to stop or hopefully not go around it because the person keeps moving. But we did have that. But the scenario we set up during the planning was a variety of situations, again, behaviors, which is what I focused on. So we had lane changing behaviors. We had to go around slower moving cars. We had to go, around static objects. There was a 4-way stop that we created in the RNDF, as you remember, the Route Network Definition file.
The map file, yeah, the map
file.
Yeah.
Which is why map is one of my trigger words because people get excited about it, and I'm like, you just need some waypoints, basically. So we had the 4-way stop, and then I also developed, again, because of my interest in the cooperative nature or decentralized nature of this system. A single AV is fun. When you get 10,000 of them together, you're going to have a parking lot unless they are coordinating their movements, right? And I've been saying this for a long time, and we're just now starting to see when the system effects when you just get a few of them together and they aren't cooperating. So I developed a cooperative behavior for pedestrian protection, and we demonstrated that at New York City as well. So that involved one vehicle with a sensor detecting a pedestrian crossing that the AV had no way of seeing with its own sensors. And the message would, we used DSRC back then for connected vehicle communication, but we also used military radio, band radios, 2.4 gigahertz, whatever, 150. And the message would go and the AV would evaluate, okay, and if there's conflict potential for a crash, it would slow down. So we had video of all this, but the interesting thing is we had planned to be there demonstrating with other vehicles from the DARPA challenges. The GM vehicle, they couldn't make it. And so the only other vehicle we had, and I don't remember if we had approached your group at all. I don't remember, but the only other group was the Stanford junior Volkswagen. So they were there as well.
Got it. And what year was this?
2008.
2008. Okay. Was it after the Urban Challenge, did you say, or before?
It was in November. So
Oh yeah. It would have been after the Urban Challenge. Yeah. Sorry. Yeah. Because the Urban Challenge was 2007. That's right.
Yep.
Yeah.
Yeah. So that, and again, we thought, the OEMs, the GMs of the world are going to want to come to us and talk to us. But 2008, everything sort of imploded, right, financially. And so that didn't happen. But we continued to develop on this Ford Explorer, and we created additional behaviors of like convoy behaviors. So cooperative following of another vehicle in scenarios where you could, offset your distance or whatever. And we demonstrated that to the U.S. military, what they called the Robotics Rodeo. I don't know if you remember those. So they had several of those, and we demonstrated the cooperative convoy. And that actually led to the program at Southwest Research pivoting to like Office of Naval Research and some other funding sources.
Gotcha. Yeah, there's so much I want to unpack here. First thing is, it is interesting. 2008 was an odd year because there was the 2004 DARPA Grand Challenge. Folks didn't get very far, but it was a significant achievement nonetheless. 2005, Stanford, they win the challenge, DARPA, and then 2007, the Urban Challenge, Carnegie Mellon, and GM, right? So, and then in 2000, and then after the DARPA Urban Challenge, it kind of like, is DARPA going to have another race? There was some rumor that they were thinking about it, but But Peter Diamandis and the X Prize Foundation spawned an effort to have an autonomous automotive X Prize, right? They were exploring this. Right. They were like, well, we think DARPA's kind of done their thing, proven their thing. Now let's take it to the next level. And myself, well, I mean, I was invited to participate. There was a bunch of, I want to say like 50, people from GM to, the folks from Carnegie Mellon were there, and all, like a lot of folks from these teams participating in like, what should this race be? And it was really turning out to be something that would have been, I think, super cool, because there was going to be two components of it. One was sort of like a cross-country challenge. Yeah. It's like the Smokey and the Bandit. Let's get the vehicle from LA to New York, right? Like that was the idea. And then there was going to be like a hyper focus challenge where you're going through like this obstacle course with rain and fake snow and tumbleweeds and whatever, chicken hawks flying at you, everything that you can imagine. And I thought, well, this is going to be really hard, but it's also going to be so cool and fun. What? But then it kind of waned because I guess that was like 2008 and 2009, and then with the Google car mention, and then folks were starting to think, well, industry is really taking this forward, and that kind of defeated the X Prize's mission for that. But I thought that would have been such a great competition. And
yeah, and that's the thing, so I was at Southwest Research, right, and it's a small, it's about 3,000 people. Their business model is to be about 10 years ahead of whatever is going on now, because that's where they focus. That's why people hire Southwest Research. They want to get ahead of things, and it's probably about 10 years. So,
and is it, do you have government or commercial do they have government or commercial folks who fund them to do things, or is it both?
Oh, no, it's the business model is you find clients, you propose, you get funding. There are no grants, no endowments, none of that.
I see.
So you eat what you win type of thing, eat what you kill. So you're pursuing clients, you're developing proposals, then you're managing the projects and working on someone else's project and doing internal research to try and where clients can't even imagine what's coming next year. That's where the IR&D program really fits in. And so like the AV program spun off a bunch of other IR&D efforts that were related. But so we're doing all this, and we're going to these robotics rodeos. We're doing convoy following. We're doing all kinds of cool stuff. Then we start getting the funding from, the military. So we took, again, this informs a lot of my opinions still today, is we took what we had developed for the Ford Explorer, and we simply modified it for a military Humvee or a small sort of tactical off-road buggy. And then we had a Freightliner that we bought, a used Freightliner, to haul a giant flatbed with all of our cool toys. And we're like, well, let's just automate that too. Like, so for us, it's like, the platform doesn't matter too much. The platform size, just your physics are different with the turning radius and the stopping distance and the acceleration. And the sensors are different because of the field of view overlap and the blind spots. But otherwise, it's still the same. You're taking in data about the world. You got to make sense of it, make a decision, and then take action. And what's interesting about that is like your behavior on a city street is very different from your behavior in maybe a hostile environment, right? So like the military is looking at vehicles that are not obeying traffic laws. I mean, you're on a trail somewhere, or maybe you're driving through a field even. So the entire world model can change. And my argument has always been that if you have a flexible behavior architecture, you get away from this discussion of sort of edge cases and stuff I've never seen. And you know what I mean? The stuff that kind of pops up in the discourse nowadays, humans encounter stuff we've never seen all the time, and we don't get stuck. And that's because we've got these fallback kind of behaviors to say, well, yeah, that's new, but it doesn't matter what that is in the road. It's a thing I need to not hit,
This work that you were doing, and I want to dive deeper into the behavior model because I think that's fascinating and the work that you were doing. But was I guess, separate from the folks who were working on perception, right? Like, is that fair to say? Or
it was all intertwined, just because we had the advantage that there weren't a ton of us. Like now these companies have whole teams and all they care about is one little slice of the pie. They only care about LiDAR processing, right? And I think we didn't know it, but we had an advantage where we couldn't specialize like that. We had to understand what the localization algorithm was doing, or the path planning algorithm, how it fed into long-term planning. And then the behavior architecture is, well, we're in this behavior. From here, we can switch into only a finite number of other behaviors. And there are specific triggers that would send us there, So we had to understand all of that. We worked together in a little, basically at Southwest, we took a building and modified it. That was just building that was available. So we're working there just all in a group type thing. Got the vehicle next to us. So we try stuff out. We loaded up, and we had simulation capabilities too, but then we'd go out to our test track and test stuff. That was kind of the process, yeah.
So you mentioned as one behavioral example, I think like passing a vehicle, right? Like just passing, I guess, passing in motion or just stop and pass, either one, I guess.
So one of my favorite litmus tests, I guess, for the maturity of a vehicle or an automated driving system is, can you overtake a slower moving object? Now, for humans, that's trivial. But if you break it down into the behaviors, you're in maybe a lane following mode. You've got somewhere trying to go and you're following a lane. And then there's just an object. You're not going to pass every object you come up against, right? But you come up and it's moving slower than you are. So then you have to make a decision. Do I sit here and travel at that person's speed, or do I go around? Now, going around then means first you have to switch into a behavior called lane change, right? And the reason it's a different behavior is because it's got a different set of parameters, different set of requirements. Lane following, you're just following the lane or GPS points or whatever you have. The change lanes, you have to evaluate if there's a lane available, number one.
Right.
Are there other cars coming in that lane and if they are, what's that speed delta? And then you have to plan a path, and you know all this, but it's called a spline. So you have to plan a path, and then you have to pass the vehicle and then do that all in reverse. And what's fascinating about all that back and forth is you have to do that and you have to decide if you have enough space to do that for your next thing that you're going to do. So imagine if you have an exit coming up. You're not going to pass them. You try to pass someone when you have an exit coming up.
Or an intersection, right? You're in the middle of it. Yeah.
And so that's it's a lot of pieces that have to be analyzed and assessed and then executed properly. And so if an AV can pass a slower moving object, that actually exposes a lot of underlying capability maturity, even though for us it's like, oh, that's trivial. You just go around them. Well, yeah, but there's a lot that goes into it.
It's interesting. And I love this as an example to kind of auger in on, because it does involve a lot of different things that you mentioned, right? Like determining if there's vehicles behind you, if it's, a lane that's running in parallel in the same direction, or if you're passing in a lane where there's opposing traffic, you're looking ahead, presumably, yes. Or you're just not doing it, depending on the rules. But then what's interesting is the question arises, you're on the side of that vehicle and you're passing, right? And then you might discover with your sensors that vehicle's longer than you thought it was, right? It's not just a vehicle. Now it's it's a line of 20 vehicles.
Yep. Yep.
And or it is just one vehicle and they speed up.
They
right?
speed up
Because they're being jerks, right? So the question is, like, in those scenarios, like, the behavior model's obviously got to deal with these situations, and what does it do, when it discovers it's a longer train than they thought, and even though they're well ahead of the intersection, now they discover, well, now I'm going to end up in the intersection because there's like 20 cars in front of me.
And this is what I mean by the difference between a flexible behavior architecture and edge case speak. You could hard code in all of those scenarios, and then you'll still be missing an infinite number of scenarios that you haven't hard coded in. So with a behavior architecture, though, you're following. You do have a behavior available to you to go around them, which means this other series of other behaviors like lane change, check. Can I go around? One of the things that we implemented early on, like before World Congress, and it's still my favorite, even though it sounds silly, it's still my favorite behavior, is called lane change abort. So think about the vehicle. If there's 3 lanes and you go from the right lane to the center, but someone else is like, yeah, that's my lane too, right? That is a conflict. And you have to abort the lane change. You have to plan a spline immediately back to where you were, maybe slowing down. And so we put that in just because we're like, yeah, that's what you have to do in the world. Not because we were going to experience that in New York City, but it's something to demonstrate. And it's something that anyone who's looking at the vehicle would understand intuitively that that's a requirement if you're going to try and change lanes.
And that abort, though, like, you could be, of course, there's is there an abort to an abort? Because, like, if you're like, hey, I'm aborting and now I'm trying to get back in, but someone comes up behind and closes you out, right? Because they pull up behind the other car and now you're locked out. Like, this happens to me all the time when I'm driving. And so, like, what do you do there,
Right. So to get back to your other scenario, if it's not exactly that abort, but if you get into a lane and you see, things change. So the world is a dynamic thing, and you have a dynamic actor next to you that may respond to your behavior by speeding up, or there's a whole line of cars. The decision could then be, well, now I can't get around this thing, or multiple things before my exit. So I have to get back into the other lane. Now, a simplistic approach would be, I'll just turn on my signal. Maybe someone will let you in, maybe they won't, right? You start slowing down with your signal on, and then if there's a gap, you can pull in over. A more aggressive approach behavior would be slowing down and coming over even if somebody's not kind of letting you over. That's not a good idea. That's what people do, though, right? So you have to kind of think through these things, and it's not that you want to hard code in, okay, this is what we do in all these situations. It's the vehicle has to react to what's in front of it, and that can change on a dime.
So how do you implement? And by the way, I guess, because you're a nonprofit doesn't necessarily mean, or it was a nonprofit doesn't necessarily mean this stuff was open. But are these algorithms open to see, or are they they were just for customers? Got it. Okay.
Well, and since it was internally developed, it was IP of Southwest Research, right?
Okay.
When we went on to develop more for military applications, the rules are different. It's like,
of course, yeah.
One of the challenges that we were presented with, it was, this Ford Explorer is great. So we have, here's a military Humvee, an older one, here, we'll give it to you. You can't use LiDAR. You can't use radar. Those are active sensors. You can't use those in a hostile environment. Can't use GPS. Probably not there. You're not going to go pre-map the environment. So that's an extreme example of taking in information about the world with a limited sensor set and then making decisions and acting on it in a different set of rules than changing lanes and taking left turns on green.
So this is an interesting sidebar now, because it is the 20-year anniversary was October 5th of 2005 for the DARPA Grand Challenge 2005. And of course, DARPA is always out there 10, 20 years, right, to try to get ahead of and bring technology into defense applications that could be advantageous. And some of those rules that for deployment that you mentioned, like you can't use LiDAR, radar, GPS, or maps, like every team in the DARPA Grand Challenge used LiDAR, radar, maps, and GPS. So like, why wasn't that a rule for DARPA? Like, if that's really and is that still a military sort of constraint? Because it seems like that's really over constraining, but maybe, I mean, there's probably a good reason for it.
Yeah, and that was the challenge they presented to Southwest Research, not what is potentially doable, but what is the extreme. So if you do have a vehicle that does have active sensors, maybe it's not out in a hostile war zone, right? Maybe it's actually just driving stuff around a base or between bases. I don't know. Whatever application you might think of. The convoy concept was interesting because like the concept of platooning evolved over time to mean vehicles traveling very, very close to each other, right? But for me, that was never the platoon or the convoy. A convoy is just a group of vehicles traveling together. And in a military convoy, you don't want to be bunched up. You want them spread, right? So you can't just take out one and like three others go type thing. So the way to think about it is different. I think DARPA, back then, the amount of work that we did to accomplish what we did probably wasn't feasible just to put out as an open challenge and have people respond. It's just, that was like the hardest of the hardest problems, right? And so this was like 2010, 11, 12 in there that we were doing that. And we were successful. And that's kind of informs my opinions now too. Yeah, that's an extreme. I don't recommend camera only. I think AVs should have multiple sensor types. But I know it's possible. I know it's possible for a vehicle to have a plan where it's going. It looks at the environment. It can figure out its way through it. But we did that. It's not easy. And it's not even practical probably most of the time. But it's possible. So anytime we need to use these other things, and this still gets companies in trouble today, right? I think you guys are really good at avoiding this pitfall or trap. Is that like GPS and localization? GPS is a tricky signal, right? Sometimes it's degraded, sometimes it's absent totally. You have to have a way of sensing your motion, what's called relative localization. So tire movement, your pose in the world, so that you know where you were 10 milliseconds ago. Whereas companies or ADS stacks that rely on GPS as a fundamental requirement, when GPS is funky or disappears, they stop. They can't function. Is that's just what GPS is gone? Well, I don't know where I am anymore. Even more. I knew where I was 5 milliseconds ago, but I don't. So those are some of the things that I've seen evolve over time. And I still see in the industry, I still see a lot of reliance on things that are helpful and are great to use if you have available. But when those things aren't as solid as they think, or you think they should be, you get bad things happen. And we haven't seen broad system disruptions yet because there aren't enough of them out there.
Yeah, and I totally agree. And of course, depends on how much the customer wants to spend and what they're doing at a particular time, because it's like this weird moment in time where there's a lot of companies still, certain organizations doing pilots and they only want to spend so much and some want to spend more. But I believe, the path is not just redundancy of sensors, which is important, but of course, redundancy of algorithms, and like localization is a great example. in an environment, in a particular environment, you might be able to rely on GPS 98% of the time. Who knows, right? Might be less, might be, more, but let's say 98% of the time, GPS with RTK, corrections or something. And, but then, what do you do that 2% of the time or 5% of the time? Well, there's lane keeping, right? It's another method of localization. You can kind of know where you are laterally and keep going forward. And then, well, what if you don't have lanes? Well, then you can use maybe SLAM, simultaneous localization and mapping, where you've got sort of mapped areas, especially where there's no outages. If you're going into a tunnel, you can just look, to the walls and and what have you. And then, there's other things like ultra wideband. If you're in a garage, maybe you could use that. But like these layers of localization, and of course, each adds cost. I mean, certainly ultra wideband is going to add cost to your deployment. Lane keeping may or may not add much cost because it's there, but you might have to keep your lanes fresh, right? But you have to have all these things, and then maybe you gracefully degrade. If you're cruising along and you've got like a solid GPS RTK signal, and then it disappears, and then you're looking at lanes, if they're really crisp, maybe you cruise at a certain speed, but if they're a little, worn, as is the case in a lot of cities or wherever, then maybe you slow down your speed. And so it's graceful degradation. And I think that's key. And the problem is when you go into these deployments is, does the customer want to test all of these, and can they test all of these sort of variations? And if they're and then a lot of them are like in the transit space, well, we're going to have somebody on board anyway. Yeah. So, and that's a whole other topic I want to talk to you about, but like, it's like, well, okay, in these certain areas, it's like it's an L4, L3 system to, you drive. And these are decisions driven by, customers a lot of times, or just, budgets. But I think that the holy grail, or what you need to do for L5, is to have all of those methods of localization, and then safety watchdogs and all kinds of stuff, redundancy of sensors and algorithms and controls, right?
Yeah. And so you think about how do humans drive? Whenever I hear the argument, so a lot of our clients are state DOTs or transit agencies, and whenever, the question always is, what do we do with the infrastructure? And so my argument keeps coming back to, the infrastructure should be good for humans because that will benefit the AVs as well. So if the lanes are bright and crisp, then humans benefit, and then machine vision benefits as well. When that isn't the case, because it's not always the case, in fact, it's quite often not the case, how do humans continue to drive? We use a lot of environmental cues to figure out where we are, where we need to be. So I grew up in Colorado, and I learned to drive in the snow. And when you're driving on the snow, what's fresh on the highway at 20 miles an hour, you can't see them. There are no lane lines, like no road, right? So how do you know where to drive? Well, there's a car in front of me. First of all, I'll follow that car. Or if there's nobody, maybe there's some tracks in the lane, and I'll follow that. And if it's bad enough and it's like a 2-lane road, right, I'll drive in the middle of the road. No, I'm not going to try to stick to the lane because I'm going to end up in the shoulder.
Right.
So there's a lot of like flexibility in the rules that we use. But we use all these environmental cues. So like sometimes my car right now has lane keep assist, right? So it kind of nudges the wheel whenever I get too close to a lane line. Well, it does that even when it's not really a lane line. It's a tar thing on the road that's been, maintenance for repair for a road, or there were lines there, but they're shifted because it's construction. And the ADAS system is still picking up the lines and saying, hey, stay here, where I know, well, yeah, those are markings, but those aren't where I'm supposed to be following right now because there's a concrete barrier right there. I don't want to go into the concrete barrier. So it's that it's that type of what are all the cues that I can draw on. And the perfect scenario is a GPS, bright minds. Okay, great. As you start taking those away, though, take away GPS, you're in a tunnel or under an overpass. GPS will also disappear sometimes. The lane lines they're bad, or there's construction. Do I gracefully degrade to the point where maybe I pull over, but maybe that's not even possible, or maybe that's dangerous, right? If you're in a tunnel, you can't just pull over. There's no over. So then you get to the question of, well, if you can't gracefully degrade, then you ungracefully degrade, which is just causing some kind of e-stop or something, right?
Yeah. Yeah. Fail safe. Yeah. Well, we have that luxury with ground vehicles. We can stop and not fall out of the sky, like with airspace. But, so just getting back to the behavioral model, cause like that sounds like that was your bailiwick and your interest and focal point. Like, can you give some sort of sense for like how this worked? Were you using like neural networks? Was it a rules-based system or rules engine that was off the shelf, or something that you coded? Like how did it work? Kind of in a nutshell, like if you can, speak to just the, the basics.
Sure. And it's funny because the discussion nowadays of artificial intelligence, machine learning, all deep learning, all these were fairly novel, new words way back when we were doing all this. And yet we were doing that. We were doing AI, we were doing ML. It just wasn't called that, right? So we weren't using neural networks in a formal sense. The behavior architecture for us was more of kind of like a Markov model. So you're in a behavior, from that behavior, you can switch to other behaviors based on a trigger or a threshold. So software-wise, if a specific trigger comes in, you essentially go over to another set of modules that has its own kind of litany of things, but another trigger could come in that kicks you out of that to go over back to your original set of modules or a different module. So we would develop these behaviors that were like modular, that could be accessed by the perception system, the path planning system, the control system, any of those. Because at the end of the day, all of that stuff that's going on in the computer ends up at the wheels as either accelerate, stop, or steer, or don't do anything.
Yes. Speed or steering, speed controls or steering. Yeah. Maybe shifting,
yeah,
rarely so. But so interesting. So now some of those inputs, these triggers, would obviously come from the environment, like sensors and what have you, and some might be internally, I guess, could be internally generated. But like, so how did you, to give you that flexibility that you're kind of speaking to? Like, did you manually define those triggers, or was there like, I'm going to learn what these are kind of things?
So back then we had specific triggers that were defined. If we were to do it today, we'd probably introduce more of a learning system. And this was, we were using a modular programming software. It was basically C++, but it allowed us to do, it had a visual front end. And this was before ROS. So if you're familiar with ROS, of course, the robot operating system, which is neither for robots nor is it an operating system, but never mind that. ROS is a publish-subscribe architecture where modules publish information, other modules subscribe to it, right? We were kind of doing that before ROS came about. So like, I'll give you a concrete example. So four-way stop. When you approach a four-way stop, we're in this behavior of a four-way stop. And that's different than a two-way stop. It's different than a yield. It's different than a traffic intersection. So like a traffic intersection, it's red. You pull up, you have a stop point defined, and you're sitting there waiting for the trigger to go, which is a green light. In a four-way stop, you come up and stop, and you have to have, before you stop, you have to have identified who else is there, because that tells you the order of precedent of who gets to go first. Well, we all know from our own experiences that sometimes people go when they shouldn't, or they don't go when they should. Now, so that's where the behavior triggers come in. So I come up and I stop, and I know the person on my right is supposed to go. So I wait for them to go. That's my trigger to go. But I'm not going to wait for 30 minutes, right? That person's like talking on the phone or watching a movie or they're paying attention. So then I have a timeout. So I'm going to wait for 3 to 5 seconds. And if they haven't moved, that's my trigger. Now I go. That's how these triggers can kick us into and out of other, behavior modes.
Gotcha. And this was all, like you said, 2008, 2007-ish kind of stuff. Interesting. So, yeah, because I guess Ross came out in like 2007, I think. I don't even remember, but like it was really immature when it first came out, and it's and arguably still limited, but yeah.
Right. And we actually ported all of our code to Ross around 2010. So we were evaluating it when it first came out, but then we actually made the switch in 2010. So the four-way stop example, though, let's say you decide to go and you start turning, but then the person decides they're going, right? And they start to come out to cut, they're going to cut you off. Well, now the behavior isn't, well, what's the world, coming to, and what's this guy's motivation? There's a crash possibility. The only response to that is to stop, right? So that's what you do. You decided they weren't going. You start to go. Then they cut out in front of you. You stop. And when they pass, then you go. I mean, these are all just very simplistic behaviors that you can chain together into more sophisticated behaviors. So
you said there wasn't, like, you didn't want to hard code this, but these triggers, were they coded, like, or were they like, how do you not hard code these triggers? Like, what in what form do they come from? If you're not coding them, or maybe you are, I don't know.
Yeah. So I think back then we were coding the trigger, the thresholds and the triggers, but they were flexible, so we could adapt to things that were happening, in the world as they happen. So, for example, on the convoy system, we would test where another vehicle would get in between us and the vehicle we were following. Well, then you fall back on another behavior, which is vehicle following. So I'm still following that vehicle because they were using communication to know where they were. But now there's an object in front of me. My sensors are telling me, and I have a parameter in my system that says I need to maintain X distance from vehicles at whatever speed, so that person gets in between you and you back off. Now that has ramifications for real platoons or convoys on the road. And that's partly why a lot of these companies, I think, were chasing, we're going to drive 10 centimeters from each other so people don't cut in between. The problem there, though, is like when you get like the freight trucks, right? You get 2 or 3 of them, pretty soon you have a giant wall traveling down the highway.
Yeah.
People can't permeate that system. They have to go behind it or in front of it. And that's going to cause a lot of undesirable behavior where people are like, there's an exit, but there's 3 freight trucks I have to either get in front of or behind. I can't cross over. So side conversation there, but yeah, the behavior triggers are, again, whenever there's an object in front of you, you need to react to it. Doesn't matter what it is, doesn't matter what, why it's there. It's there. So if you've decided you have the right of way on a 4-way stop, but then there's suddenly something crossing in front of you, doesn't matter what it is, why it's there, you're just going to stop. You're not going to hit the object.
It's fascinating. So, that's all. So, that's a good description of, like, your interest, as you mentioned, in behavioral systems and creating, modular methods for dealing with that. And then you kind of like I guess from there was like sort of this evolution in, it sounds like, of your interest into cooperative autonomy, or maybe it was always there. And you've written about decentralized control and emergent stability. First of all, like, what are, if you could say for everybody who's watching, like, what are those, and what do these ideas look like in real world autonomous, like, traffic now?
Yeah. So decentralized. So control systems can either be centralized, decentralized, or some hybrid of those. Decentralized means that there's no single point that can control. So you have a bunch of independent actors that are interacting with each other. What's fascinating is, based on the way they interact, the question is, does the system have a goal, or is the goal just simply emerged from the interact? Those are two very different things. And so the concept of emergence pops up with the study of behaviors, study of decentralized systems. Our traffic system is literally a decentralized system, and therefore the emergent behaviors we see are things like congestion. That is literally an emergent behavior, because emergent behaviors are behaviors that aren't defined at the individual level. So there's no traffic congestion defined for an individual driver. Congestion only emerges as an interaction of the drivers in the environment. So that's the basic concept. And so if you have AVs that are driving around like humans, only using their sensors, reacting to stuff that they can see, you're not going to have any better transportation system. It could be worse because the AVs don't understand fully the context of why humans are doing things. They might be more hesitant because, risk aversion. Great. But if you can get them to not only exchange information, but then coordinate their movements, then you start to get system level efficiencies or effects that are beneficial.
Got it. So looking at, like, stuff from a, it goes up to some cloud, and then there's some network of they're aware of where congestion may be, like with a Google map today, right? You see the red spot, and you don't want to go to the red spot. You might take a different route or something.
Yeah. And it's even more fundamental than that. So again, I go back to insect behavior. Ant colonies and beehives. We all kind of know about them, but most people don't really know, like, how do they do what they do? So as an example, they don't communicate the way we understand, right? They leave pheromones in the environment, and then other individuals pick up on those pheromones and then react to them. So just based on that one little bridge of information, when you get thousands of things doing that, you get an emergent behavior at the system level. Now, is it just chaos, or is it, doing something? And so my interest in grad school was, well, let's say we know what the end goal is. How do we design the individuals so that the emergent behavior is what we want? And that's what the military is very interested in too, right? You have a bunch of AI or automated things. The system, we need to control the parameters of what the system does. That is an emergent behavior exercise.
Right.
So there are different ways to know things too. So we could do communication up to the cloud, this type of stuff. We could do communication directly between things.
Between vehicles, yeah.
And then the other way is simply, the word is stigmergic. And it's
what is that word? Sorry, say that again.
Stigmergic.
Stigmergic. Okay, I got to look that one up. That sounds like a good name for a band.
That is communication via the environment only. So this is how termites communicate. They don't communicate directly. If I'm a termite, I move something or I change something in the environment. Someone else comes along, sees that change, and makes an additional change.
I see. It's like a hobo, right? The hobo.
Yeah.
Puts the mark on they put the marks on the house, and then the other hobo, I don't know if these are a proper term for this these days, but like, I've seen that, right? Like that's how you sort of you mark the environment, right? And then something else comes along and does something based on that. Interesting.
So if you imagine I like thought experiments because they help explain things that you get out of the black magic of, software. So if you imagine my role is to pick up green squares, green cubes, and put them somewhere else. Then you've got another person like me. We don't talk, but that person's job, if they find a green square, they add a blue sphere on top. That's all they do. So they're just looking for green cubes and they put a blue cube. Then you have another person that says, well, if there's a blue sphere on top of a green cube, I'm going to add a yellow triangle right next to it. So pretty soon, and then you've got someone else that says, yellow triangles are bad. I'm going to take those away. And so you get lots of those interactions and you get something happening. And then the question is, what is that something and is it desirable? Evolution with insects, they've evolved to accomplish things. So another example I like is the colony defense mechanism. So bees mostly, but ants also. Well, ants and bees. Okay. When you disturb an ant nest or a bee hive, why do they all come rushing out? Right? Who broadcast over the PA system that there's a danger? Well, the first ant or bee that is bothered, they release a pheromone that's an alert pheromone that says, bad. The nearby ants and bees pick that up and they send it out. And they say, I've found this alert pheromone. There's something bad. So it propagates very fast. And their response to that pheromone is to come out as fast as they can and find whatever's causing this issue. So that's why if you disturb an ant's nest, you leave it alone, after a while the pheromones wear off because they aren't getting reinforced.
I got it.
Because if I still feel threatened, I'm going to keep putting that pheromone down. But if, I'm not threatened, okay. Yeah, and then the pheromone dissipates and everybody goes back to what they're doing.
So I got so excited about learning this new term now, stigmergic, and the relation to hobos so how does it relate to, so can you tie it back to like these traffic systems and how to control autonomous systems? How does that apply? It's such an interesting concept that I've never thought about it. It's a bio-inspired thing. It sounds like that you could apply to traffic management. How does that work?
So you can do a Google search for the stick pulling experiment. That is one of my foundational studies that talks about and shows how stigmergic communication works. So it's these little square robots that drive around on a little platform. And there are these pegs sticking out of holes. So, this is a robotics issue, right? So that's why roboticists and entomologists are actually close cousins. They study each other's worlds. The little robot finds a peg, it pulls the peg up, but it can't pull it all the way out because the peg gets stuck. So it sits there and waits. And if another robot comes along, finds the peg, the combined pulling will pull the stick out. But if it sits there and waits long enough, right, a timeout threshold, it says, this is a lost cause, lets it go, goes on to look for another peg. So why is that interesting? Well, they aren't communicating together at all. And the success of the system to remove the pegs, right, that's the goal, is dependent on how many robots you have, how far away they are to travel to find each other, and that timeout threshold. So if you set that timeout threshold to 1.2 seconds, you're probably never going to pull pegs. But if I set it to 10 minutes, every peg that's sitting there getting held is one fewer robot looking for a peg. And let's say you have 10 pegs and 4 robots. They all find a peg and they're all just sitting there holding it, right? But if you have 2 pegs and 10 robots, you're very likely to get both pegs pulled. So it's got a lot of really interesting pieces to it. Now, I will say stigmergic communication is probably the least efficient unless you've got thousands of things like termites. But for traffic systems, it's not good. An AV would see a change in the environment and then react to it, which is really not much better than just what we do now, right?
Well, this goes to, there's this whole V to X communications infrastructure. VX could be V to I for infrastructure, vehicle to infrastructure, V to V, vehicle to vehicle communications, V to C, vehicle to cloud.
Yep.
Maybe there's some other variable for X. I don't know.
P.
Pedestrian, vehicle to pedestrian. There you go. And so what role do you see? And I guess there's like some SAE standards, but also these V to X communications playing today. And why has it been so slow? Why has adoption been so slow in the US and maybe elsewhere?
Yeah, there's a lot there to dive into. Let me start with so SAE has done what they can to try and develop standards around wording. There's a standard called J3216, which deals with cooperative driving automation, CDA. However, like a lot of this stuff, I take issue with it because they have 4 classes defined in that standard. A, B, C, D. Class A is status sharing. That's what it's called. Now, this is me telling you that I'm here or that my speed is 25. I don't care if you're listening or not. I'm just telling you. Okay? Class B is intent sharing. That's me saying, I'm changing lanes. Again, I don't care who's listening. These are not cooperative behaviors, right? This is just me broadcasting out. And that's the problem, the fundamental problem in my mind with the concept of connected vehicles. There isn't a collaborative layer on it. So
there's no handshake. There's no handshaking of some sort, right?
No. So there's just broadcast, right? And the assumption is that information is absorbed and acted upon. But that's a giant assumption. That's why it's been slow, I think, to adopt, because the equipment has a cost to it, right? So OEMs don't want to add cost to their vehicles. Nominally, it's a more safety device, so that usually has to be mandated or as the regulatory processes. And in recent years, the OEMs all communicate to their own cloud anyway through telematics. So the vehicle to everything can be accomplished through other mechanisms, not just direct. But that gets into other problems. So let me continue on with J3216. Class C is the first class I would say is cooperative, because that is coordinating your movements. It's called consensus seeking. So that's me saying, I'd like to change lanes, and you saying, well, I'm already here. And me saying, I still like to change lane. And you saying, okay, I'm slowing down so you can change lanes. And then I say, great, I'm changing lanes. That is a class C. That's cooperative. Class D is what I call hierarchical. And that's more the military or platoon type of thing where, yeah, we're all communicating together, but I call the shots. I'm the lead. So I tell you, you can follow me or you can't, for me to maintain some distance or whatever. So that's that class.
I see.
And so none of this. So the communication mechanism or protocol doesn't matter if there's no cooperative layer on top, no application,
right,
that is allowing collaboration.
Yeah, and then underneath the hood, there's been a little bit of a rug pull with DSRC. DSRC was this, I guess, communicate the underlying protocol communication standards that was going to be like the thing. There were mandates, and then that was pulled. And then there's a switch to now CV2X, which is cellular, I guess, communications. And I've heard, there were some political reasons for it. Who knows? I have no idea. But the bottom line from a, practitioner / supplier point of view is there was that change, which really kind of like, you had customers investing in this DSRC setup to get started. And now it was just this, now you got to switch to a new thing. And it was, there's a cost to that. So What are your thoughts? Like, why did that happen? And are we at a stable underlying standard with CV2X?
Yeah. So that, for us, again, back to Southwest Research, when we were doing cooperative vehicles, the connected vehicle thing was also kind of just getting started. I mean, it kind of started in the late 90s, but not really took off until early 2000s. And what I always tell people is to remember that the concept of connected vehicles that the US DOT put forth was a concept that predated smartphones. So the idea was, we've got a radio, it talks to another radio, we've got all these standard messages, and that kind of made sense back then, right? But then I think technology sort of overtook things. And with the smartphone model, you have apps, right? So the hardware itself, you got the hardware, which is like, it'll work with any of these apps. The apps are what you really care about. What does the hardware do for me? Well, it can do lots of things because I just downloaded an app. So we continue on. Mandating stuff is a little tricky because the USDOT doesn't want to pick winners and losers, right? So DSRC was a specific, it's what it is, it's a frequency domain. That's what it is. Now the FCC controls who has access to frequency, right, in the US. So it just didn't materialize for different reasons, probably just a lot of different socioeconomic reasons. And so the FCC basically said, well, we're going to take a big chunk of this and give it over to the Wi-Fi because it's adjacent to the Wi-Fi spectrum. So that's kind of how that came about. Now, we still don't have CV2X, devices in cars, right? And again, it's the same problems of an OEM is, it's extra cost for them. They already talk to their own crowd. There's cybersecurity issues with any of this stuff. And there is a security credential management system, SCMS, for as a layer for this communication protocol. But again, all of these topics, the hardware, the communication, the cybersecurity, all of that's ignoring the application.
Yeah.
So what is the application? And especially in a cooperative sense. So I actually worked for General Motors for a couple of years after Southwest before I came to AECOM. And it is tricky. It's tricky because as an OEM, if you have a message coming into your car from outside the world and it's not from your OEM cloud, I mean, are you going to trust that message? It's hard. It's hard.
Good point. That's a really good point. Yeah. Interesting. Well, that's a good segue to your work at GM. I mean, you worked on AI and machine learning, right? Fusion architectures, I guess, for things like, was it like road surface friction?
Oh, yeah.
Then, so how do those systems, how did they at the time, and I don't know what time period this was specifically offhand, but how did they learn to feel the world, like, at that point?
Yeah. So that was an interesting time. GM had just acquired Cruise, not too long before I joined. However, they were still pretty separate entities. And so I was working for the GM IT actually department. There's a big office here in Austin, and I interfaced with engineers at GM, not so much the Cruise, which were mainly based in California. So I was working on, after Southwest, I was bringing my knowledge of these systems. One of the products I did work on was, we called it low mu. So mu is, for those who are indoctrinated, mu is the Greek symbol you use in mathematics for lots of things, but for engineering, it's friction. So low mu surface, low friction surface. Basically, how do we detect ice that's ahead of us?
Right.
When you're on ice, you know it because you're spinning, right? But for an AV with cameras, a radar and LiDAR, what can we use to detect the ice or slippery road prior to actually hitting? So that was probably my first time of applying more machine learning techniques and I worked with the engineers, because the vehicles were in Michigan, so I didn't have access to them. But I had the sensor suite and everything. And what I did is I proposed, there's a specific term in machine learning, I forget what it's called now, but it's kind of the idea of the multi-agent system, which is what I was really interested in grad school, where you have agents that cooperate together to do something. Well, in machine learning, you can have a voting system where each agent kind of votes, and you have a way to then say, based on all these votes, I think this is the reality. Because in truth, all these sensors are really good at during certain times and conditions, and then really bad at other conditions. And so you have to kind of take what they say with a grain of salt in those conditions. Well, you can't, the conditions always change. So with the voting type of style, we got it working pretty well. And I made a point to say, look, in an ADS system, you need to have stuff running at about 10 to 15 hertz at least. I mean, so this algorithm couldn't take a minute to decide there was ice coming up when you're traveling 30 miles. So we had the voting agents, and it based on the reflection, if you're, and the reflection of the sun plus a reflection of the LiDAR, you could start to learn what ice looks like when you're approaching them. It's still tricky because if it's ice covered with snow, it's like...
Yeah. No, I mean, I can't see, with our human eye, right? It's hard to see ice on a road and you just... I guess it's interesting to some extent. You that it from just a weather condition that it just snowed or it just sleeted, and so and it's the morning, or it's the getting to be the night, and to just drive slower. It's like interesting. It's like it's really just based on, to some extent, cloud data, if you will, weather information. And because it's almost impossible. I can be cruising down in Virginia especially, and I'm sure in other parts of the country, you're cruising down a country road and it's shady and you hit a patch of ice when it's otherwise clear, and
you can't see that, and there's really no sensors that help you detect that either. You can get close, but like what you brought up is actually a really good point. Is we use probabilities in our decisions, right? We factor in all these things, like at the morning. Well, what does that matter? Well, that means that the sun hasn't been out. Well, what does that matter? Well, sun can melt. It's that logic chain that we take for granted. So the vehicles, if they do need to use those probabilities of temperature outside. Okay, we can either use a thermometer to get that, or get it from a cloud system. What's the temperature and humidity? That tells me if there's likely to be ice. What time of day is it? What, is the sun out? This type of stuff. And that gives me a probability that ice is possible. The other thing that we did with that system, though, is we tied it into the control system of the vehicle to detect slippage of the wheels. So we have a prediction of what's coming up, and then as we pass over it, we get feedback from the wheels, and that updates our predictive ability for you know what I mean? So it's that feedback.
Right.
And so if we say, hey, there's ice up there, and we flip, and like, okay, good guess. But if we say there's nothing up there, and then the wheels are turning, we're like, okay, bad guess. Let's update our model.
It's interesting because, and this has probably always been the case, because anything that's happened that people are doing today probably has been done before in some incarnation. But like with generative AI, I'm seeing more of a, versus say 2 years ago or 3 years ago, more of a pivot towards this co-piloting concept. Like, hey, generative AI alone, just don't rely wholly on the machine, but it's really good for human machine cooperation, right? And so like, for example, in this example, the vehicle could say, hey, based on morning conditions, this is going to be a little icy. I'm going to apply this I'm going to be a little bit more cautious. And then maybe the human can say, no, I'm going to override this because I happen to know I'm going to be taking a route that's, not an issue or whatever. But like that's sort of like in giving, that sort of co-pilot function, humans, machine sort of cooperation, I think, is a good practical path for bringing this technology into the fold, as opposed to just it be all human, all machine, one or the other.
So you say that, and I'll tell you why that won't happen, and it's because of tort law.
Thank you, lawyers, right? Yes, let's blame the lawyers. I agree.
Because these systems, that's the problem with like level 3, as SAE defines it. Who's in control? And blame can be spread across multiple parties, right? But when you're in a level 4 AV, the AV is supposed to do everything, and it can ask you to take over, but you don't have to, that kind of stuff. You can still take over. So here's the thing. You have a data recorder monitoring who is in control. Is it the software or is it the human? And at the time of an incident, that is going to become critical. So like level 3 is problematic because you're not supposed to have to pay attention necessarily, but the vehicle will ask you to take control when it can't figure something out or something looks weird. But humans can't. You can't reassess a scene fast enough, but it can just like give up and give you back control even though you're not ready. So it's problematic, but that's really the question for these things. So the Copilot is great, but it might be more like almost like verbal. The car's still in control, but you're like, no, I think we can go faster.
It's a really good point. And, and it's like, while it's certainly intuitive with respect to generative AI right now, this Copilot mode, and whether or not that should apply to, vehicle automation is, it's intuitively could make things safer, right? Because it's redundancy. You have human beings and then you have the machine kind of like working together, and it's a form of redundancy, and it should make it safer. But yeah, it's like, oh, but like then who do we blame and who do we collect money from when something goes wrong is sort of the pickle there.
Exactly. And that,
yeah.
It's just, and then insurance.
Yeah.
There's a lot of issues, just a lot of those issues that pop up that have nothing to do with the technology per se. They're really more how our society is organized, and, when something happens, we need to figure out what happened and why, so we can prevent it again. So who's in control is kind of the linchpin of that question. So like for AV transit, we advise on that quite a bit. If it is a level 4 system, which is kind of the only ones we deal with, yes, the operator can take control. You need operator training to know when and why to take control, because if they take control, the liability shifts from the software vendor or, deployer to whoever kind of owns that operator's service. It could be the transit agency, it could be a third party. And so if they just take over because they feel like it's going to do something weird, and then they hit something, they're in control at that moment.
Right.
Now that doesn't mean, let's just let the vehicle hit something, because then they'll be liable. That's where the fuzziness comes in, and they took over because they were going to hit something and they ended up hitting it, but they had to take over.
So you mentioned something that's interesting too, with respect to, you want to know if something goes wrong, why did it go wrong, right? So that you can fix it. Yeah. Here's an interesting thing with neural networks. If it makes a wrong decision, perceives something wrong, says was not a human being there when there really was, or whatever the situation is, the neural network doesn't make the right decision and it leads to an accident. You can't, right? You can't look at a neural network and know, you can't answer the question why it made the wrong decision, because it's just a bunch of numbers. And so there's no way to verify and validate that it's correct, and there's no way to know what it did wrong except to kind of like retrain it and hope, I guess, that it's going to get it right the next time. I mean,
Well,
what are your thoughts on that? Like,
that's the trouble with just neural networks. In general, there's a whole area of AI called explainable AI that has popped up in the last 10 years, which is neural networks or other models that are explainable. They can tell you exactly what led to decisions. At Southwest Research, again, we weren't dealing with any of this neural network stuff yet, right? But we did have another spin-off internal research project where we tried to do this. We tried to trace the why, because the why, we actually had an incident that was internal, no injuries, but it exposed a weakness in our architecture. And what's interesting is I saw that exact weakness exposed by a AV freight company in the news 15 years later. So I recognized it immediately. NTSB got involved. They determined that it was what happened to us. So backing up, we did an internal project to figure out exactly what signals were, not only the sensors, but what decisions were made by what modules when, because unraveling that to find root cause can be almost impossible, even if you don't have neural networks. So the why is very tricky unless you build your architecture with the mindset of we want to be able to dissect decisions. So if you just have a black box neural network, there is no why. It just popped out.
yeah,
You have to have something that is tracing the steps and it is interrogatable, to get to that why.
right. Put it under the light and let it sweat.
Right.
And ask what it did, and it pops out some numbers, and you're like, well, change those numbers, I guess. I don't know. It's hard with a neural network in that sense, but I mean, I think obviously they are so compelling and so useful in so many things. But with regards to these systems, automated driving systems, where ultimately, verification and validation should sort of factor into everything when you get to a level of production, especially, it's question.
Networks, that's fine. But, any of those things, they should all be part of an ecosystem. And the watchdogs you mentioned earlier are one of the most important things.
Yeah.
Having watchdog, which are basically modules that are just keeping track of something. So we had even in Southwest Research, right, 2006, we had watchdogs that were watching the GPS signal. If it dropped 2 or 3 packets, that's a problem because, we have to make sure the relative localization is on par. The signal, something people don't really realize unless they've worked on these systems, is all these sensors and other things are all happening on different timescales. LiDAR comes in at, 12 hertz, 12.5 hertz, 25 hertz, whatever. Cameras, 30 frames per second. The IMUs are dumping 100 hertz of data, so the modules that are getting all this data at different times have to sync it all up to make a cohesive view of the world for the decision modules to make sense of it all, and one of the other ways AVs fail is they take too long in that step, and they don't pass on relevant information to the decision makers fast enough. So again, if I don't want to bring in specific events, but certain events where the system was trying to decide what was in the road versus there's something in the road we're going to hit, let's not do that. That process took too long and, an accident occurred. So all these sensors and decision modules are all happening different timescales. So unraveling the why can be very difficult unless you have a sophisticated watchdog system that's kind of logging a lot of this stuff so you can reproduce it.
Yeah. Kind of related to this, is there an area of like autonomy or robotics, AI, that you think is sort of underrated or under-researched that could more attention right now?
Yeah, well,
But like maybe this explainable AI or whatever. I just was thinking about that.
I think that is an area that needs more work. I think, just especially in like safety critical systems, you can't have black box decisions. You just can't. And that's why a lot of safety critical systems are still like hardwired, transistors, essentially the flip switches, because you just have to have certain parameters come in, certain parameters always come out. So for any kind of AI system, it has to be some sort of mechanism to interrogate why signals were sent, why decisions were made.
Right.
So as a personal note, our incident at Southwest Research, we eventually discovered that a buffer had been overwritten. This happens all the time in software. And a command that was maybe 5 minutes old had gotten to the controllers. So the controllers reacted on a command from 5 minutes ago, and the world changed in those 5 minutes. Right?
Yeah.
There was an AV freight company no longer in existence that had made the news because they changed lanes, almost hit a truck, and then hit a concrete barrier. They figured out, and to me, it looked like it was merging, right? It looked like a merging behavior. Now, there's multiple failures here, but what they found was that the command was 3 minutes old.
Wow.
But when they merged. So A, you have to check timestamps of the information, but B, it did almost hit a vehicle. So something failed there to say, yeah, I've got a command to merge, but there's a car right here. I shouldn't run into the car, right?
Like the subsumption architecture that we refer to, like we have prioritized behaviors, right? Like collision avoidance is ahead of lane change, and
that's what I mean by behavior triggers. Like, I'm lane changing. Oh, there's an object there. Let's see. That takes precedence over lane changing, right?
Yeah.
Hitting objects.
Right. Yeah. Yeah. It's interesting. Well, you're at AECOM now, which is a wonderful organization, and it's right at the intersection of infrastructure and automation. What does autonomy look like to you when you sort of zoom out from the vehicle to the whole city, as you kind of considering things nowadays?
Yeah, I'm in a great position, actually, I think, with my background, because one of the main things I do is I help clients like state DOTs, transit agencies, kind of see past the smoke and mirrors and the marketing pitches that they are inundated with, and help them understand kind of what the capabilities of this technology really is. Because the big question keeps coming up, how do we plan for this? So hundreds of millions of dollars are being spent planning for a thing that doesn't exist yet, which is automated vehicles. And so there's a lot of misconceptions. Well, AVs are going to be this, they're going to be that. It's like, we don't know yet. So you want to plan for it, that's fine. Or there are automated buses, let's say we want to deploy. Okay, let's do that. Those are realistic. So yeah, AECOM is a huge architectural engineering firm, civil engineering, basically. Build, design bridges, roads, all kinds of stuff. And that's not me, obviously, but the thing about my world is that the technology aspect has now intersected the world of infrastructure to a point that it's becoming disrupted. There's always been this concept of intelligent transportation systems, IGLs. So those are like cameras and other sensors and signs and all this great stuff. But that is still focused on a human behavior model in the vehicle world. As you start to get non-human drivers, this is where my passion for decentralized systems comes in. Our whole system right now is built because of human behavior model drivers. All of our modeling, VisSim, Transmodeler, all these have human behavior models built into them. The AVs are not human. They're not human. They are something different. And right now there's only onesie twosies. So we're not seeing system level effects. But if we start to get more and more with system, behavior will change.
Yeah.
And it's an open question whether that's good or bad. We want it to be good. So back to my stick pulling experiment, it's like, we know we want a good transportation system. Let's start there. How do we get the agents, which are the vehicles, including humans still, how do we get them to interact in a way that doesn't give us a mass parking lot on every hour?
Well, we're both involved in, you're involved in a different capacity and like with transit and transportation agencies, but what do you think? What are your thoughts from your sort of perspective on how do transportation agencies think about what they're getting like right now when they order AV systems versus the reality that they've experienced, in the last, decade and more recently, and then, what are they expecting when they order these vehicles at this point? What are your thoughts on that? And how does it differ from reality?
So I think there's a variety, there's a big wide spectrum. So right now you can't order these vehicles necessarily. You sort of can. It's starting to become a thing. There's still a question of who's liable, who's deploying. The agencies aren't deploying these vehicles. Someone else is deploying them on behalf of the agency. Or the agency has a third-party operator company that has to be trained about how, when to take over, why you take over, all that stuff, right? The routes are real-world routes. They just are the real world. That's what I love about the real world. It doesn't care what your marketing pitch says. It doesn't care what you convinced investors of, right? The real world is what it is. So the vehicle, if you're going to put it on this route, and it's called an operational design domain, is what SAE calls it, right? If your environment that you're operating in contains these characteristics, your system has to be able to do that. So that can be everything from GPS degradation to random pedestrians always crossing the mid-block, right? So I think trans agencies' interest has fluctuated between, this is a new shiny toy, right? It's interesting, to it's actually a piece of our deployment strategy. And we do argue at AECOM that the reason a bus operator can't necessarily be removed is because they do a lot more than just driving.
So that's an interesting thing. I mean, they do more than, you've said it right there. They do more than just driving. They, might help people get on and off the bus if they're ADA compliant vehicles, and help people if they have a medical condition, all kinds of things. If something's gone wrong, there's, a bad actor in the bus, there's somebody there. So will these transportation agencies ever take the driver out of the seat? And if not, what's the return on investment? What's
Sure. That's the big question always, is what is the automation providing beyond what we have now? If you don't remove it, right, if we just look at investment, what is it? So one thing automation can provide is actually more consistent and safe driving. Not that bus drivers aren't safe. They're probably safer than your typical human, just public driver. But driving a very large vehicle like that, with human eyes and mirrors, and without any kind of ADAS system like we enjoy in our cars, right? Like emergency braking, just not even in buses. I learned that recently. It's kind of sad, but so the driving task can be more consistent, smooth, et cetera. That in and of itself could be a benefit. Will drivers ever not be there? Probably. I mean, we have trams and people movers and other stuff that don't have an operator. A lot of airports have the people movers. You could certainly have a person there doing it, but it's not needed anymore. So whether they're there or not, I don't know. Let's still to be determined in what the role is. Right now, they're really still needed. Even if you have an AV that's very capable. One of the things that's interesting about transit specifically is bus drivers are pretty good about when they're approaching a bus stop, if no one has requested a stop and there's nobody at the stop, they probably won't stop, right? It makes them a little more efficient otherwise they're stopping at every stop and nobody wants that one. Now, if there are people there, they're pretty good about noticing the person looks up, goes back to their whatever, right? They're like, that's not one. Or people look up and they're like, start getting their stuff ready because it is their bus. These are very subtle cues.
Yeah.
So an AV, the reason it ties back is, okay, you have an AV. Does it stop at every stop? Because your on-time arrival is going to be horribly quadruple.
Right. Well, it may be that the operator becomes someone who's like the guy or gal who's on the trolley in San Francisco, right? They're there hanging on and announcing things and sort of being the eyes and ears while the vehicle is navigating. And I do think just ADAS is a great thing that can be brought into these legacy platforms right now. It's available, it's something that's doable, for when the driver's on board. You've got then this vast data collection system too with LiDAR and cameras that can be collecting information for security or post-processing reasons. And then, when it gets into a bus yard, it can go self-park, it can wash itself, it can do all these things, or there's a hybrid automated mode, whereas it's going through a tunnel, it's just driving, whatever, there's, I think this is where to me, that's the co-pilot model to some extent, right? Where you're letting the technology help you. And then in places where it can be automated, it can go and be automated. And this is all, more possible now. Like it is possible now versus like, hey, I'm just taking the driver out of the seat like tomorrow,
Stop example, you could have a screen that is waiting for the human prompt. So it's going to stop, but the bus driver can say bypass.
Yes. Yeah.
And then it's like, great, bypass, we're going on. So, so that's a co-pilot version. Yeah, I agree. But the other thing that is interesting about, let's say buses, specific rates, at AECOM, we started as automated bus consortium to 2019. I was looking at the specs, right? The performance specs to put out there for others to respond to. One of the things we decided against, like that, or that absolutely needs the driver, at least today, is imagine, or one of the reasons we excluded bike racks is we're imagining an automated transit bus where someone's trying to get their bike on or off of those front racks and the bus doesn't understand that and starts moving or tries to move or something. Like there's some nuance there, right? So, well, maybe you put the bike racks inside the bus then instead of on the front. Maybe that's good. Well, okay, let's just think about doors. The doors open. When do they shut? I mean, if someone's trying to get on, let's say, and they're on a wheelchair or just like having trouble getting into the bus and those doors start closing. I mean, then, okay, now we got to put sensors to type the doors are clear. It's just all of these issues that a human just does no problem.
Right.
So if you're going to automate, you have to automate everything, to work.
It's a good point. It's a very good point. Yeah. Yeah.
Like the robotaxis, they don't have that problem because you open the door and then you close it and then it knows you're ready to go.
Right. Robotaxis and cars also don't have other problems that buses have, in that, forward collision avoidance or AEB, you can't really just slam the brakes, right? Because there might be people standing up or sitting sideways. And so it's a different sort of method for stopping.
The standing issue is very important. If you do have a wheelchair, there is actually a product from a company that starts with a Q.
Q constraint. Yeah. Q strain or something. Yeah.
Yeah. Constraint that'll automatically secure, a wheelchair. Again, stuff like that we don't think of is different than a passenger vehicle, way different from Navy freight, right? They all have their own different constraints and even regulatory bodies. That's another point to make, is that the robotaxis, transit, and freight or goods movement are very separate worlds.
So these, public transit is subsidized, pretty heavily, right? It couldn't. I mean, I don't know. I don't know the economics very well, but I've heard, it'd be difficult to do this without such subsidies, if not impossible. And so how do these agencies, how can they go from, having a handful of automated vehicles or one or two, in a pilot, to getting that fleet level benefit? What unlocks that on the commercial and the organization side to enable that to happen in this space?
So I think what's interesting about transit is the Federal Transit Administration, FTA, pays for about 80% of a bus. So a bus is about $1 million. I mean, they're expensive things.
If it's not electric.
Yeah, right. That's just a normal standard bus. So an FTA pays for a good chunk of that, and then you might have some other sources to help that. But the utility of a bus that does stuff by itself, I think, still has to be proven. We're all working on this in different ways, you and I, but the business model or the business case has to be there that this additional expense is beneficial because X, Y, Z. And that could come from a lot of different directions. But you're never going to get to a fleet if you can't prove out the utility of one or two. Because at the fleet level, you're going to have emergent behaviors that we need to consider. So if you imagine a yard where all the buses are automated, again, without a cooperative aspect, and it could be a centralized system in a yard. It's a dispatch system. You could tell bus A to go here, B to go, or C to sit still. You can do that. But that application layer has to be where, otherwise the buses are all kind of moving around and getting each other's way, and we can't quite figure out who's supposed to go to the wash station yet.
Right. And then in parallel with all this, with the rise of, the likes of Uber and Lyft and those services, ridership, I guess, has been impacted. And you deploy these, I guess the question arises, when you deploy these automated vehicles, does it increase ridership? Does it, what if the ridership isn't there? How do you increase ridership, for people who, and get to the people who really need it?
That's why I've seen a trend actually in the interest of AV transit in more of the microtransit, on-demand model versus the circulator. Because the circulator is just a route that it always runs, and it depends on who wants to get on that route. Yeah. Whereas a microtransit like May Mobility, that's what kind of one of the things they've done. You've seen their minivans essentially, or some others have done similar things where it's more of a small vehicle. It's not a full-size bus. Maybe a cutaway style, like where we see at airports. I know you guys have done. So that model where it goes from point to point because there's a specific demand, not because it's just out running around, right, with no passengers. So right. I've seen a shift towards that. And I don't think that TNCs, the traffic or network companies like Uber and Lyft, I don't think they eat into transit necessarily. I think these are different roles. And so then the question always has to come back to, what is the purpose of the automation? And as long as we can answer that question, then I think it's pretty easy to sell. It's when you get into a situation of, well, here's this cool shiny object, what the heck are we gonna do with it? That's when it's a little harder.
Right. Right. Well, it's all interesting, and just sort of, thinking about the future of all of this. We hear about level 3, 4, 5, like level 4 and 5 in particular. Do these definitions even make sense anymore? I mean,
I've never liked the definitions. And again, at Southwest Research, I was there when 3016 was born, right? They are as good as they are, and they're a good way to sort of corral the language. But what I've seen is people misuse the levels. They weaponize the levels. Yours is a level or not a level, whatever. People make up levels that are in between 2 and 3, this type of stuff. So I think they're
like fractional levels, like 2 and 3/4.
Well, I've heard people say L2 plus or 3 plus, and it's like that's not a thing. I mean, I understand what you're getting at, and what they're getting at is more the capabilities, and that's really, I think, what we should focus more on is what's the capability maturity of the system, and it really, the one thing that I do like about the standard of SA is that it does tie everything to what's called OEDR, which is object and event detection and response. Again, all loaded words, but it just means what is the capability of the system to perceive its environment of objects and event and then respond to those appropriately. So like ADAS systems are very narrowly focused. Emergency braking is literally just looking at, your speed and distance to something in front of you. And it doesn't care about anything else going on. Lane keep assist is just looking for those lines, and it'll just nudge that steering wheel once in a while. Then you get level 2 stuff, which is like GM Super Cruise, right? Where it's a mapped environment, it'll drive there and only there. And it still wants you to kind of pay attention. It'll track your eyes, but you don't have to touch the wheel.
Yeah.
So as we go up in these levels, though, then it starts getting fuzzy. It's like, and then the branding, that's what drives me nuts the most, is companies brand these things at a higher level than they really are, a higher capability maturity than they really are. So I think the levels are here to stay. I spend a lot of time trying to, tell people what they do mean and what they don't mean.
Yeah. Yeah. I mean, it is more of a spectrum. I mean, like, it goes back to to some extent, what behaviors have been sort of deployed and what ones have not been deployed, and I've seen companies, and I know we encountered situations where it's like, there's a behavior that we have, but we're not going to turn it on because it involves a whole level of testing and things like, like passing, right? Like the passing behavior, right? Like, okay, we can do that, but, to deploy that, like, is going to take a lot more effort and verifications and things like that. And anyway, it's just an example. Like, I think companies encounter that, and agencies need to know, it's more than just these sort of discretized levels. There's,
and again, it goes back to my behavior architecture focus. So if you go to one extreme, you've got a people mover, APM, automated people mover. There's mature standards for those things. They sit on a track or rails or whatever, but they just drive it. They've got, no operator. It's very simple. So that on the one extreme, right? And then on the other extreme is something that doesn't exist yet, maybe, but let's just say it's a human driver is on the other extreme, right? We're not necessarily cooperative, but we can pretty much drive in any situation we want. So in between there, you have a spectrum of maturity. And in my mind, the maturity relates to how flexible is your behavior architecture, right? So like a people mover has like 2 behaviors, go and stop. That's it, right? It doesn't care about anything else. Oh, and open door signals, open and close doors. As you go up though, and you have to add behaviors like traffic signal interaction, other intersection types, stop signs, yields. The more ambiguous the situation is, the more maturity you need. So a stop signal, if you're just going straight, is a simplistic behavior. It's green or red. You just have to watch for stuff in your way. Other vehicles, pedestrians getting in front of you, whatever. If you're turning right or left, though, that starts to get more complicated.
Right.
if you're in an ambiguous situation like a four-way stop or an yield or a roundabout, that takes more maturity. Merging is a good example on a highway. Like you're speeding up, the other cars are going pretty fast. You have a limited window to make decisions, and you have to be able to do that. So AV freight, that's the world they're living, so they're okay with it. But a lot like robotaxis, they're like, oh my god, highways can't do that, right? I mean, they will eventually, but so that spectrum of maturity. Now, an AV freight isn't going to navigate a roundabout necessarily, right? So because we're living within the world. But you go from the automated people mover to human drivers on a spectrum, and then we can define levels, but it's really for the environment and the use case. Is the behavior stack sufficient?
Yeah. And then there's just it's also ties to a specific environment in some cases because, you might have as a feature traffic light detection, right? And it's like, and we think of traffic light, the traffic light has got a nice crisp red, green light. And then we go to, there's a certain part in Philadelphia or whatever that had these really old traffic lights, and I couldn't see them with my decrepit own eyes, right? Or they was hard, right? Yeah. And then because they're old and they were dim, they were being replaced, but they were going to be replaced like later. And it's just like, okay, those happen to be lights that we have traffic light detection, but we can't see those lights. Wow. Or we just can't we don't, I don't know what percentage of the time we would be able to see them, so we have to run through tests, and you've got to vet it in that environment. And that's just like one simple example. It's like you have a feature, but does that feature work in this sort of situation where the light is just, the bulbs are dim and the lights and the sunlight is shining right on it, and there's trees hanging over it, and
And again, it all ties back in my mind to how do humans do this? We don't just stop. We might slow down because we can't quite see it, but we look at what are the others around us doing? Are the other cars going? Is the cross traffic going? Probably I shouldn't try to go,
Yeah.
What's interesting to me about signalized intersections is the signal detection is only one aspect of it, right? So the detection tells you certain things about approved movements, right? But if you can't see it, then what do you do? Or let's say it's doing something weird, like flashing red. That's weird.
Right.
Wait, red. It's not red. It's, that is a four-way stop behavior. So that's why I say you go from traffic signal behavior to four-way stop behavior.
Right. Yeah.
And so it's no longer a traffic signal. It's a four-way stop, but only right now. It could be fine.
Well, what excites you the most right now in autonomy and AI, and some of the things that you think are gonna really sort of accelerate things? What kind of keeps you the most optimistic about all of this in the autonomous vehicle space? Yeah.
Again, you and I, we've both seen this stuff kind of ebb and flow, and then there's a lot of interest, and then it kind of these companies come and go or whatever. I do think that transit has a very good future for this as a use case. I think goods movement also could, but it's got its own regulatory system, right? And then the robotaxi model is driven by, do people want to take these vehicles or not, right? And all of them have different drivers, like economic drivers. I think if I could say my excitement is that the vehicle systems are getting more mature. They are being able to deal with the real world without requiring special infrastructure, special modifications to the infrastructure. If that's possible, great, let's do that. But to require that automatically limits you, right? So if your system will only work when the lines are painted pink, then you're limited to wherever they paint pink lines, right? But if you can deal with any color at all, then you can pretty much drive wherever there are just lines on the ground, that type of thing.
Yeah.
the generative AI thing, I think, is one of the things I see most useful about it is potentially in producing a lot of simulated tests quickly that the software can run through to learn very quickly. And then, of course, the downside is the generative AI making up stuff that's just not there, and then the vehicle learns the wrong decisions.
Right.
So
It
that's the
hallucinates, and there's all of a sudden you're trained to look for the 5-legged deer. You know that.
And anything else is fair game. Yeah. So we got to be careful about that. But that's kind of my excitement, I guess, is that people are for so long it's worried we couldn't get anybody's attention, right? That everybody's like, well, I don't know. And now we have transportation planners, we have cities, we have civil engineers, actually now looking at this because where clients are looking at with cities, the DOTs, they're like, wait, okay, so this technology's here. I do try to keep people from chasing the shiny object, but I want them to stay focused that, it's here, great. Let's not worry about the one or two that are running around. Let's worry about when there's lots and lots of them. Okay, what guardrails can we put in place to make sure we get the system we want?
Right. Interesting. Well, you've had, this has been such a great conversation, Paul. I appreciate your time. And you've done so much. And again, we've both lived the 20-year journey, 20 plus year maybe journey. And by the way, I saw a great meme recently from this guy. It's a picture of Willem Dafoe, like looking young, and he's sort of like he's all happy. Like it's from one movie, and it's like this is like robotics as a hobby. And then the other picture is like Willem Dafoe in this movie where he's like got this beard, he's like this old man, and he's all worn out. It's like robotics as a profession. And to some extent, I'm like, wow, that hits too close to home, But what do you, given all the things that you've done, and you've achieved, just so much. Is there something that you're looking forward to, like, really sort of, that's gonna come out, something that you're working on, that you're passionate about, that in the next, couple years or whatever, that you'll say, wow, this is, that's just exciting you right now, that you can leave people with to remember, be motivated as to what's coming ahead that motivates you.
So I keep telling people I'm going to retire on this stuff. I've been talking about it for 20 years. I'll probably retire while still talking about it, because the cooperative aspect is still just not on anybody's radar. Mm-hmm. And what I'm excited about is to see that change. So, and it will change whether I want it to or not. Like eventually everybody's going to be like, oh my gosh, there's a lot of these things that are causing these, but we're starting to see those little system effects now where you get 5 or 6 together doing something not good and the whole system gums up really quick. So my excitement is that we finally get to a point soonish, I think, where not just communicating of broadcasting, it's not cooperative, but actually a collaborative architecture on top of these vehicles, so that they can participate with humans, not gum up the system, and actually could make the system better. There's been a lot of modeling and simulation that show AVs could perform traffic calming on the highways, so to prevent, the onset of congestion. So there's a lot of things that can be done, but it has to get to that point where we have an open conversation about what is cooperative vehicle.
Well, it's a beautiful vision. It's a good way to end this podcast. Thank you, Paul, really, for your time. It's always great talking to you. And I appreciate it in this context of venue here. Lots of good stuff.
Thank you for inviting me. Appreciate it. Yeah.
Thank you. I hope you enjoyed the show Driven with me, Paul Perrone, your host. Don't forget to check us out at driven.show on the web and give us a thumbs up or subscribe here if you like the show. Thank you for listening in. See you soon.